And today we're talking about what the most studied planet in our solar system is. So, Nick, what is the most studied planet in our solar system?
Well, I think about a lot of things that we might study. Like we study the sun, we study the moon. Of course, those aren't the most studied planets, but we see them all the time in the night sky or the daytime sky. We can look at them as much as we want, but you shouldn't really look at the sun with the naked eye. I think about Mars. That's a studied planet. We really have the most
No,
studied planet. What about, is it Jupiter?
yeah,
Or
we've sent a spacecraft to Mars, and Jupiter and satellites to Saturn as well. It looks like there's a little bit of a lag, so Nick and I might be talking over each other, but we're partners in crime, so we'll carry on anyway.
Partners in science.
Exactly. But actually, the most studied planet would be our own planet, Earth. It's where we live. It's where we've always lived. It's where we hope we will continue to live for quite some time. So it's really important to understand how the planet evolves over time, what kind of processes are going on around it and on it. And one way we do study Earth is through satellites up in space. So we're looking up at the sky right now.
From here in Boulder, Colorado.
That's true. See, that's fair and field for those of you who know our university at CU Boulder. But let's move forward into the night and look up at some stars.
And so, of course, we can study the Earth just by walking around on it and doing measurements from the Earth. But we will see a little bit more once we go into nighttime. Here we go.
Yeah, there are very many fields of science that study the Earth, such as geology and archaeology, astronomy as well. Though we study the stars, we study the Earth. So we can see a lot of stars right now in the sky. And if we put up some satellites, we might be able to see them too, but it's actually pretty difficult to differentiate which are stars and which are satellites on this little screen. It's easier in person. You can see satellites moving across your sky.
In fact, there are a lot up there. You just can't always see them.
So these labels really help us.
Yeah, so at night they're moving overhead and you can see something moving consistently across the sky. It looks like a star, and the star looks like it's moving across your night sky. It doesn't seem to twinkle. It just seems like a constant dim light moving. And it's actually satellites, chunks of metal up in space that are helping us do science or communicate. And they're reflecting sunlight back down on Earth so we can see them with our naked eye.
So something satellites do a lot is receive signals, and signals travel at the speed of light. So we are going to travel like a signal and reach a satellite in the sky and get a new perspective on how we study Earth.
All right, let's journey up into space and find a satellite for ourselves. At the speed of a signal, at the speed of light, we journeyed and found this low Earth orbiting satellite. This one's known as Aqua.
Aqua, yes, you can maybe guess by its name. Aqua studies lots of phenomena regarding water, precipitation, evaporation, the water cycle, and how that works on Earth. Aqua is just one of many other research satellites we have in low Earth orbit, or LEO for short. This is a really good place to put research satellites because it's so close to home. Being close to home provides high bandwidth. There's less lag in communication.
I could use less lag in our communication.
I was just about to say that. Yeah, hopefully our satellites will be nice to us over the course of the next 30 minutes. These satellites are also more accessible for crews and servicing. This is where the ISS lives. It's also where Elon Musk's program Starlink resides, here in low Earth orbit. So this is really good for communicating with parts of the Earth. However, since it's so close to the surface, low Earth orbit satellites can only see a portion of the Earth at once. So you need a whole network of them if you really want to keep continuous communication for different parts of the Earth.
So here we're looking at all of the low Earth orbiting satellites, or I shouldn't say all, but a huge number of low Earth orbiting satellites. These are ones that you can typically see with your naked eye from the ground. And that means that if you look up at the sky after sunset or before sunrise, you should be able to see a little bright lights moving overhead. And those are probably these ones, these hundreds of satellites. And we're showing you the orbits, the trajectories they take around our Earth.
So this is one layer of satellites, the low Earth orbit, but we have some more if we zoom out.
Now those ones orbit in about 90 minutes around the Earth because they're so close, but there are some that, since they're further out, they'll take longer to orbit, and you may recognize their names as well. They orbit up here. Go ahead and tell our audience these ones.
This is the GPS system. A lot of us are really familiar with GPSs because we use global positioning for navigating to work, to school. These systems are in our cell phones and our cars. They're super cheap now compared to what they used to be when I was little. And this is the network of the receivers for those, of the transmitters for those satellites. So
it looks like a giant atom.
It does. And there are so many little strings in each kind of path. And that's because we need extra backup satellites just in case one or two go out. So you can always be triangulated anywhere you are on Earth with this satellite system.
So we need 3 of these GPS satellites going over your position, and then that they'll tell you where you are to within a few meters, a few yards of your location. But if one of those dies, you're saying that we need to have a 4th or a 5th one, as just to be redundant, just to be careful.
Yeah, you got it. So we always like having backups, just generally in most things we do in science, since they are so large scale. Backups are very useful and helpful, and especially for the goings on of large societies back on Earth. We would be a little bit lost if at this point if our GPS system just disappeared.
Now
oh my gosh, but are there more satellites, Nick?
Actually, there are a lot more satellites. In fact, out here, we can get to such a great distance from the Earth that now, at about this distance, we'd have to take about 24 hours to orbit around the Earth. The Earth would spin around once, meaning that these satellites would orbit about once every day, putting them directly above the same place on Earth all the time. As it spins and as they orbit, they stay above the exact same place, so we call them geosynchronous. They are in synchronicity with the surface. And let's throw up some of their names. There's a lot of them, you can see.
So this is a really cool visual. Hopefully, if we get a little closer to the names, you might even see some that you recognize.
Yeah, we just got to orbit around just right.
Intelsat.
There's DirecTV.
So before satellites, signals couldn't go very far because there were mountains or buildings or other terrain just blocking the signals. Now, with all of these satellites in space, they have a straight path to the sky and just need to shoot up and then get shot back down. And we can communicate over long distances, and satellite radio can bring you radio from anywhere you are on Earth, TV. We live in a very connected world right now, and it's largely because of these satellites that get to aid us in communication as well as research.
If you think about it, each one of these was a different launch, or in some cases, maybe they launched more than one. But if we see here like XM Rock, XM2 rock. This would be for Sirius XM satellite radio. Of course, we saw Brasilsat for Brazil, and we probably saw Solidariedad for different TV providers, radio providers, and some of these are even space satellites doing science. So I'm gonna go and load up one of these that is a science satellite called GOES.
These space satellites don't study Earth, but they actually study in the other direction, space. And so they don't need to be as close to Earth as the one we were showing earlier, Aqua, for example.
Right. So some of them are looking outward into space. This one I've brought up is known as a GOES satellite. It actually is looking down at the Earth and helping us measure things happening on the Earth, whether it's weather or climate, forest fires. It can track a lot of things. And right now it's in shadow. So I'm going to orbit us around until it's in daylight. We can get a good look at it. There we go. This GOES satellite, this is space agencies, the U.S. space agency, setting up a large number of these satellites to help us monitor the Earth and the things happening on the Earth, to track global weather patterns, to look for whether it's forest fires or emissions of, say, natural gas flares, lightning. They can track all sorts of things on the Earth.
Yeah, so let's talk about the Earth more in depth. We can zoom in past all of these satellites and talk about what we know about the most studied planet.
So we're going to remember that we went from the low Earth orbiting satellites to the higher Earth orbiting satellites and the GPS in between. And now we're zooming in closer to the Earth to see what it is they're studying. All right.
Actually, like this on your own computer at home. Oh, I hope that didn't break up. I was saying you can get this view of the Earth on your own computer at home. Because of all of this crazy technology we have, we can see our own home in the night sky view of the Earth, and just the fact that we can actually see a view of half of the Earth at night is really neat. And so Nick is honing in on Boulder, Colorado, again, which is where Fiske Planetarium is located.
And all of these little bright dots that you're seeing here are different cities. These are the bright night lights of the United States that we're hovering over. The different cities, the interstate highway systems. These are revealing to us the location of where people are living around the Earth and if they're using electricity to light their homes.
That's right. We can also see something else from space. We can see pretty impressive geological features on the surface of our own planet.
To do that, I'm going to see if we can't go into daylight. Oop, let's see. Gonna orbit us around to put us back in daylight side of Earth. If you ever see the Earth spinning this fast, you might be getting dizzy. All right, put us right over the United States again, this time in daylight. So now we can see the green patches representing plants, forests. Some of the oranger patches are just dirt, rock, different terrain. But what are you thinking of specifically to look at, Emily?
I think it's pretty neat how we can see the Grand Canyon from space.
I think we're almost right over it. We're kind of over Boulder, but here, if we load up this whole data set, it's kind of like our own Google Earth or like a map program. It's like we're looking down at the United States. We're going to zoom in and see if we can't find the Grand Canyon. Whoa!
If you've never been to the Grand Canyon, it's a really cool place to learn about how we can study history through looking at layers of rock and geology.
I'm lost. It's such a big world.
Nick is finding the best way to bring us in here.
Here, let's see. It's I think it's up here. There we go. If we just zoom in, I'm sure we can find a lot of different canyons and canyon structures. Beautiful. Look how pretty this looks from outer space. This is what astronauts on the International Space Station are seeing all the time.
Ah, there we go. We can see some pretty intense surface features there.
I'm going to see if I can't just shift us around, because regardless of what we're looking at, it reveals that our planet is really quite beautiful. There we go. It's almost like we're flying over our planet now. It's kind of a difficult thing to do, even doing it remotely through Zoom. But I encourage you to try to do this on, say, go to the Google Earth program. Take anything you can to just look at different places on the Earth and explore all of its different terrain and geological features. I can't do it justice here because it's such a laggy system that I'm working with remotely due to COVID-19, of course, but it's so much more beautiful to do it on your own computer.
Yeah, definitely. Always explore. There are so many ways we can explore remotely now, and unfortunately, it's not the best way, but we can learn a lot more than we might have been able to before all of these online sources were available. So another really cool thing that we've seen from space, which we're not gonna fly over or anything, but just to keep in mind, we have craters all around the world. Craters we've seen on the moon, we've seen on Mercury, some on Mars, but we have them on Earth too. And we have a great opportunity to study things that are happening on other planets, again, right here on our home planet.
There's actually one that we can see from space right up here called the 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐬 crater. If I zoom in a little bit, we can see this kind of circular ring of water. Now, this crater formed in a really weird way, but this is actually a crater you can see from space up in northern Canada. 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐬. Whoa! Okay.
That was fun. Yeah, and we can track weather patterns that are happening on Earth and how this changes the atmosphere and the ocean. Let's look at some data sets for the ocean.
All right. So if we want to look at, what are you thinking of first? We can look at things like sea surface temperature. Those sorts of things are usually measured by buoys. So we measure the Earth using not just satellites, but also a network of floating buoys in the ocean. We can measure our atmosphere using a lot of different stations around Earth that measure air.
Let's look at how we can measure and track hurricanes.
All right, so I'm going to load up here a little visual of the formation of Hurricane Sandy. And so we'll see a bunch of clouds forming up down here in the Bahamas, just north of South America. And these clouds are going to be moving north, swirling around. They're going to gain a lot of energy and crash into the east coast of the United States.
This kind of modeling is really useful for people on Earth, because seeing where a hurricane is going to head next, we can warn the right communities and evacuate towns that need to be evacuated. Hurricane tracking can save a lot of lives and a lot of property. So it's very useful to have this kind of information.
And here the animation is looped so we can see it happening again. This is all real data taken from satellites as they were trying to observe these weather systems. And they're doing this for all the hurricanes all the time. So we're trying to mitigate the loss of human life and the damage to homes and property. Of course, we can measure whether or not we're getting enough water in different parts of the United States, whether or not we're getting a formation of different cycles, climate cycles around the Earth, like El Nino or La Nina, using our networks of satellites and buoys.
We can also take a look at the atmospheric chemistry that goes on over the years.
This one is one of my favorites. I love looking at atmospheric chemistry. And so for this, to get a look at not just what's happening in the United States, just one country or one continent at a time, I'm going to do a little trick here with our system where we fly inside of our planet, like how we saw a little bit earlier. And we're going to look now at the whole planet at the same time. It's a little trick that we're doing. So now it's like we're projecting. You can see the United States, you can see South America, you can see Africa, and there's a lot of different colors swirling around here that are going to tell us something about the different phenomena, different processes happening on the Earth. And so scientists have measured these with satellites, and we're showing it to you now with very hyped up colors. What are we looking at, Emily?
So in the blue, we're seeing sea salt. White is sulfates moving around. And we have red, that is a lot of dust. You can see it's coming from the Middle East and the Sahara. What is green?
And then green is like, yeah, the burning of organic matter. So you can see there's a lot of green in the burning of rainforests. So people are burning down parts of the rainforest to make farmland. There's also just different places where forest fires have started naturally. But yeah, so the orange is the dust you said, the blue is salt, and the white is this like emissions, like fossil fuel emissions, right?
Exactly.
So what I see here is I see probably my favorite color here is the orange and the green. And so I see the orange as dust flowing from the Sahara Desert right here over to fertilize the Amazon rainforest. And so this dust gets carried over by huge winds, blowing dust off the Sahara high into the atmosphere, and it falls into the Amazon, providing nutrients for the rainforest there.
That's really neat. So let's pull up another model. We can look at now over the years how Arctic ice is changing.
Ah, yes. So let's look up at the Arctic. So we're going to go to the Great White North, eh? And here we are over, so this is just our model of Earth where we always see a little bit of Arctic ice up here. There's no land under this ice. This ice is floating in the oceans. But we can actually measure the Arctic ice over decades using our satellites. Decades now, see how it is that it's either growing or shrinking as the Earth getting hotter or colder as we measure this ice. So let's load that up. Here we go. So we're starting this back in 1987, and each time it grows and shrinks, that's one whole year. So I see a lot of the ice in the Arctic growing and shrinking as it goes from winter to summertime to winter to summer up in the northern hemisphere. And each time it shrinks, it seems to get a little bit smaller on average than the previous summer. It's showing that each year the summers are getting hotter and even the winters are getting warmer as well. So it's not expanding quite as far out as it was before, and it's shrinking even smaller each year.
You can see in those little pools between land, they don't always even cover from border to border as they used to.
Yeah, there's some places where this ice is on land, so I misspoke earlier. And yeah, they're definitely not reaching as far as they were before. So I think this would be about 1990, 1991, 1992, 1993. And we can see that as this ice is retreating and retreating, it's even retreating on land, as Emily pointed out, it's retreating in the seas. And this actually is leading to a feedback loop, is what we call it in science, is that as the ice shrinks, it actually makes it so it's reflecting less sunlight into space. The bright white is reflecting so much light all the time that it helps to keep our planet cool. But as more and more of it shrinks, we actually reflect even less sunlight, so it gets even warmer. And it becomes each year it becomes a problem as it reflects even less. It becomes even warmer, so it reflects even less, so it gets even warmer.
Yeah, so we can see in this data how the climate is changing before us in the span of smaller than lifetimes. We have a climate model we can look at as well to understand this even better.
Ah, yes. So this climate model is this is taking, oops, hold on one second. Let me play the correct one. This is taking from even this one's off a little bit. Hold on, I need to fix this really quickly. From 1870, we're going to be modeling climate as it was in 1870, all the way up to the present day, and then beyond, all the way to the 2100s. There we go. So looking down at the United States now, we're looking at colors that are mostly these greens and blues, and these are showing colder temperatures. And as they become more yellow and red, we're seeing it get warmer and warmer. And so this whole thing will last about 1 minute, and by the end of the minute, we'll have reached the year 2100. So we can watch how the climate on the whole Earth is changing using data from the past and using modeling of the future. So all we need to know here is that the red on over land masses like the United States here, and Canada, Mexico, this is showing the temperature increasing. It's getting warmer and warmer. And we've reached something like the present day here. And as we keep emitting greenhouse gases and the planet gets warmer, right, we reach that deep red color where the Earth has gotten really hot, about something like 10 degrees centigrade warmer.
So these satellites that help us predict how, these satellites that gather data for us and models that help us predict what will happen to our planet in the future are going to be essential in guiding us on how to mitigate climate change as we move forward over the next few decades.
And in fact, I should correct, I meant 10 degrees Fahrenheit warmer. But yeah, so as the climate, this case is showing the worst possible scenario where it seems like the population keeps increasing, people keep emitting greenhouse gases, and the climate gets worse and worse and worse. But what if we were to do something to try to stop climate change rather than just do business as usual? We would see the temperature wouldn't increase quite as much. So the past is still the same. We can't change how much the temperature's increased already. And we can't change how much it's going to increase in the next 10 years or so. But over the next 100 years, we might be able to make a huge impact to reduce the amount the climate warms up. And we can do this because of these satellites allowing us to measure how much the Earth is changing and how fast it's changing. So in this case, we won't see those deep red colors appear. The Earth will manage to stay a consistent temperature.
So hopefully we will do our best to change what humans have been doing the past few decades and give our scientists a run for their money and do even better than their best modeling.
That would be good.
That would be fantastic.
The models so far show that we are not necessarily heading for this kind of model. So we have to do a lot to help stop climate change. And so far, the models that they made, even back in the 90s, are showing to be pretty accurate. So that's a good sign. We know we're on the right track, that the satellites that we launched decades ago are already paying off in helping us model to understand our climate on Earth all the way here in the 2020s.
Yeah, these satellites pay themselves off many times over with the lives they save and the prevention that goes into a lot of natural disaster impact on human lives and infrastructure can be prevented by having these this data and these models to allow planning ahead of time.
Not to mention the GPS satellites help me get to my dentist office or something.
All right, so that is all we have for you guys. Thank you so much for exploring with us the most studied planet, our home, Earth. She's beautiful. So now we can take any questions you have. And I will also consult with our lovely question monitor and see what she's got for us from the chat.
So Sam asks, what do you think about the future of space and the debris we are putting into it?
So there is debris in space, and the best way to approach it is to try and mitigate space debris as much as possible. We don't want to pollute our surroundings just as much as we don't want to pollute our home.
Yeah, so these satellites that are doing this good work for us become the debris of the future if we don't take care of them. If we don't, there's no trash, it seems like, in outer space. We either just throw them deeper into space or we just leave them out there. What do we do with a satellite? Well, in this case, these orange dots you're seeing on the screen represent different debris around the Earth that is built up. And of course, this debris can be really small, like the size of just like a bolt or a nut, and just like a fleck of paint even could count as debris, or it could be as large as a completely dead satellite. So if a satellite were to re-enter the atmosphere of Earth, it's going so fast that it ramming against the air of the Earth will burn it up and break it into pieces, and it will essentially that becomes the trash. Is it just burns up in the atmosphere and disintegrates? But that won't work so well for satellites that are so far out. So we do have to somehow mitigate those because if we keep polluting outer space, there eventually won't be any space for us to put satellites up there. We've already seen satellites colliding in the past, leading to even more debris. And that debris might lead to even more satellites. It might collide with other satellites, leading to more debris. So we need to be very careful about not polluting outer space in a way that we can no longer clean it up or launch things into space of future science satellites ourselves.
Right, because as we've been talking about, these satellites are super helpful to us, and it's not just like, oh, let's just launch one, launch another. We really have to be mindful about what we're doing as scientists.
Mm-hmm.
We have another question. What did some of the first satellites around Earth do? Well, the US's first satellite was Explorer 1, and we discovered the Van Allen radiation belt with Explorer 1. The first satellite that wasn't the US's, it was actually the Soviet Union's, was Sputnik 1, and we could gather data on the environment on the environment of the atmosphere and learn about more than we ever could before. We could send spacecrafts up. So these satellites were able to tell us so much new information that we couldn't previously study because of the limitation of being on the surface.
And what we're in fact celebrating is that April 12th is going to be what is known as Yuri's night, to actually celebrate the first human into space. So the first satellite in space was Sputnik, launched by the USSR, and the first human in space was Yuri Gagarin. And April 12th represents, I think it's the 60th anniversary of a human going into space. The first human in outer space, 60 years, April 12th. I hope you're celebrating just a few days.
It's crazy to think so much of our knowledge about space now was gathered in the past 70 years, maybe. And it's a ton of knowledge.
For sure.
So,
all right.
Last question, I believe, unless there are any more. How much does it cost to send a satellite into space? Well, we've got to take in the cost to build the satellite and to launch the satellite. The ISS, I know, cost around $150 billion, a very expensive project as it was built to support human life. However, there have been tiny satellites. What are they called?
CubeSats.
There are even smaller ones.
Oh, thinking like the ones like the size of like a nickel, like little sensors.
Microsats? Chipsats. There are chipsats, and they're about the size of your headphone case, and they can cost like $100. So it's crazy the range. $100 or 150 billion. Average satellite for what you're going for with in those that Nick was showing orbiting around Earth are probably tens of millions of dollars on average.
Yeah, the average is about $10,000 per pound. So if you want to send us 1 pound of water, a pound of feathers, doesn't really matter. Whatever you want to send into space, it costs 1 pound. It's going to cost about $10,000. So that means if you want to say launch like you want to launch your grandpa into space or something, you're going to have to pay quite a lot of money. If you want to launch your trash into space, it's also going to cost a lot of money.
Do you want to launch your grandpa into space, Nick?
Actually, I think he might enjoy it, but not without actually putting you in a capsule first. So that actually, the metal, the carbon, all of that's going to cost a lot more too. Millions of dollars. You see how it very quickly balloons in cost, because to launch something that's the size of a football field, like the International Space Station, which has, can have half a dozen people on it, you can see how this costs millions of dollars very quickly. And you do this for 20 consecutive years, you're talking about billions of dollars. But of course, it's already paid off.
All right, do we have any more questions about our planet or satellites and how we transmit information, the information we can gather about Earth and data sets, all of that?
All right, well, this has been a pleasure for you all to join us on Dome to Home this week. Thanks for exploring our most studied planet with us, the Earth. I've been Nick.
Thank you to Nick for navigating and co-writing this presentation with me. Thanks to Rami for answering questions and attending to all the stuff behind the scenes.
Next week, we'll be covering a little bit more about the Earth, because this is Earth Month, and of course, we want to build up to celebrating Earth Day on April 22nd. We'll end up talking about the future satellites, the future missions of Earth. We'll talk a little bit more about the different data sets and different stuff that these satellites help us measure, and some of the top discoveries that they have made, that we've actually made from outer space or about our planet.
Right, so join us next week to learn more about Earth and the top discoveries we've found from studying.
You can hook up with us on social media, so try us at Instagram or at Fiske Planet, and you can, of course, subscribe to our YouTube channel if you want more updates. Thanks again to Rami, and that's all for now.
Bye, everyone.